Okay, so let us continue and make a move from analytic to algebraic aspects of Painlevé equations and going all the way and talking about affine Weyl groups and non-abelian discrete systems that are related to Painlevé is Irina Bobrova from NPI in Leipzig.
Yeah. Thanks a lot for the introduction and for the invitation. Yeah, I'm gonna talking about my recent research on non-abelian discrete systems that we can obtain from a affine Weyl group structure. Well, yeah, and our main example is related to the Painlevé equations. Yeah, as we already know, Painlevé equations define new special functions. Yeah, and in the case when we consider second order ODEs, we have 6 classes defining the Painlevé transcendence. And we know that Painlevé equations are one of the most important objects in mathematics and mathematical physics, and they have various commutative, non-commutative analogues. In particular, they can be generalized to the quantum case, to the matrix differential case, to the non-commutative differential case, and also to the matrix difference case and non-commutative difference case. Let me write down some example. So in particular, for the Painlevé equation, in classical case, yeah, thanks. It has this form. But yeah, now we can ask, what if we replace our function that depends on the variable z by the matrix valued function? Yeah? Then we can obtain matrix Painlevé equation, and it turns out that it could be of the same form. Where we have, yeah? Square? Yeah, thanks a lot. Yeah, and one more feature of this non-commutative case is that we know that Painlevé equation can be obtained as a reduction of the Korteweg-de Vries equation. The Korteweg-de Vries equation has the same has a matrix analog in the has a matrix analog, and it also can be reduced to the Painlevé equation. But in this case, we can obtain an additional constant of integration, which is just an arbitrary matrix over the field C. Yeah? So now we can go further and ask ourselves about what if we replace our function y and variable z by non-commutative variables. Yeah, and this is the setting in which I'm working on. Yeah, as I said, some of the Painlevé equations are related to non-abelian PDEs, non-abelian PDE and difference PDE, to the Riemann-Hilbert problem, to the orthogonal polynomials, to the Calogero systems, and etc., etc. Well, this is very huge area of studying non-abelian, or better to say non-commutative Painlevé analogues. Yeah, we know that in the commutative case, discrete Painlevé equations can be were studied by grammatists in Romani. They considered some kind of discrete analog for the Painlevé test and obtained a huge class of the discrete Painlevé equations, but without any understanding of their nature. And later, by Sakai, it was realized that these discrete Painlevé equations can be naturally obtained from by using some kind of geometric method, which is inspired by the series of papers of Akamoto. And it turns out that this stuff can be generalized to the non-commutative birational geometry, and we have some recent developments thanks to Akonkov and Reins. Yeah. So, but yeah, in the non-commutative birational geometry is some kind of a complicated stuff, and unfortunately we don't have any exact examples in this case, and this is why we wanna consider algebraic approach. So in algebraic approach, we have two very famous papers by Noumi and Yamada. They introduced affine Weyl groups method, which can be applied, to the obtaining of the Painlevé equations, of discrete Painlevé equations. And it turns out that even in matrix case, the Painlevé equations have the same Bäcklund transformations, at least the same, and the same affine Weyl group structure. So now we can ask, what if we generalize this affine Weyl groups, affine Weyl group method to obtaining non-commutative discrete Painlevé equations? So yeah, our global goal is generalize the Sakai's approach to the non-commutative case in order to obtain the classification of non-commutative version of the discrete Painlevé equations, because we know that they are more general in the commutative case. And our local goal is to generalize Noumi Yamada's approach to the non-commutative case, because we want to obtain good examples of non-commutative versions of the discrete Painlevé equations. So, and here are our results. So we can, we can generalize this the Noumi Yamada approach to the non-commutative case, and by using this, we can define non-commutative discrete systems. One of these, then we can apply this approach to obtain non-commutative analog for the discrete Painlevé equations of the additive type. Thanks to the paper of Bernstein, Shochkin, and Grigoriev. And one more example is related to the non-commutative dressing chain in the Noumi Yamada variables. So we can introduce it by looking at the Lex pairs. Then we can study Bäcklund transformations, and as a result, we can obtain a related discrete dynamic. So let me show you the main example of my talk. But before we go further, let us consider non-commutative setting in which we are working on. So we are working on an associative unital division ring over the field C, which is equipped with a derivation. Some notation. We assume that all Greek letters belong to the field and all elements belong to our ring. So the derivation is d sub t is a C-linear map from R to R, that satisfies the Leibniz rule. And we also assume that T is a central element. Let us recall that Painlevé equations are non-autonomous equations. Here I have said, but and for any constant, we have that d over this constant is equal to 0. The last thing in this setting is that on R, we have a transposition which acts trivially on the generators of R. And for any elements from our ring R, we have this formula for the action. So I don't want to specify the generators of our ring, because this description will be much more complicated, but I encourage you to think of the ring as a generalization of rational functions over C to a non-commutative case. Okay. So let us look at the example. Consider this a second Painlevé equation in the non-abelian case. So here, Q and P are non-commutative variables, and T is a central element. Alpha 1 is also a central element. So we can, in fact, we can assume that T is a central element, but a little bit later, I will show you why it's not a good idea. So let us set that the sum of alpha 0 and alpha 1 is equal to 1, and let us introduce this function f, this element f. Then we can write down these Bäcklund transformations for the second Painlevé equation. Yeah? And one can verify that these Bäcklund transformations form an extended affine Weyl group of type A1, similarly as a commutative case. Okay. So now we can look at the translation operator that acts on the parameters according to this rule. Yeah? Okay, this is similar to the commutative case. And then if we apply this separator T for Q and P, we can obtain the discrete dynamic. Yeah? And finally, the discrete Painlevé equation, which is related to the second Painlevé equation, can be written as this system. And it can be called as dp E7 system because if we look at the commutative reduction, this system coincides with the dp7 equation from the Sakai's paper. Yeah. Well, yeah. One more line about second order difference equation, but it's not really necessary. Yeah. Now let me show Lex pair for this discrete system. So one can also consider the corresponding non-commutative discrete linear problem. Yeah, here lambda is a spectral parameter and it belongs to the center of our ring R. So if we write down these two matrices over our ring R, A and B, then one can verify that the compatibility condition of this system free is equivalent to this discrete Painlevé equation, non-commutative Painlevé equation, thanks to the fact that the commutator is a conserved quantity of this map psi. Yeah? And if T is an element of our ring R, then this commutator is no longer the conserved quantity. Yeah. So in this case, we don't have a Lex pair. Okay. Next question is related to the continuous limit. So one can also consider non-commutative analog for the continuous limit. Yeah, we just introduce this change of variable with the commutative parameter epsilon, and we need to supplement it by these maps. And the function f should be chosen in such a way that we can take this limit. So in particular, in our case, we can consider this substitution, and one can verify that after taking the limit, we obtain this system that is called the Painlevé first system in the Hamiltonian form in non-commutative case. And one more question about the Hamiltonian form. It turns out that we can write it down, that we can present the Hamiltonian form for this discrete system. But in order to do it, we need to use non-commutative partial derivatives introduced in the paper by Kontsevich. So we can do it as follows. Let f be our element from R, and non-commutative derivatives dq of f and dp of f can be defined by this identity, where it's assumed that additional non-commutative symbols dq and dp are moved to the right by cyclic permutations. So it means that by taking this extended exterior derivation, we define our in the extended derivation, we're working with functions with elements up to a commutator. And so we know that in the classical case, in the commutative case, we can study Lagrangian or Hamiltonian formalisms for the discrete systems. So here's very nice review by Veselov. So similarly, we can define a discrete difference system of Hamiltonian type as follows. If there exists an element H that depends on the variables Q and P bar from our ring, and if the given system can be rewritten in the form 8, we call this system Hamiltonian. Well, again, in particular, for our example, we can present this Hamiltonian, and for the thermal logarithm of p bar, the element, for the thermal logarithm of p bar, we need to define the left or right logarithm derivative by this formula. So yeah, and I need to say that this Hamiltonian coincides with the Hamiltonian in the commutative case presented in the paper by Masa, Sakai, and Sakai. And yeah, for this Hamiltonian, we can compute non-commutative derivatives. They are given by this formula 8, and we can see that system 8, sorry, by formulas 9, and we can see that system 8 is equivalent to the DPE7 system. So, what is the main message of this part of my talk? So, we can apply affine Weyl group methods to construct good examples of non-commutative difference systems that can be integrated, that has Lex pair, continuous limits, and Hamiltonian form. So let me show the main setting of our construction. So yeah, let me briefly, or not briefly, yeah. So let me briefly recall what is the affine Weyl group. Yeah, we fix the Cartan matrix. We have two sets of roots, simple roots and simple core roots. We can introduce rooted core root lattices. They are related by pairing. Yeah, then we denote by W the Weyl group. Yeah, where all exponents are determined by this table. Yeah, and also we consider that. Also, we know that these generators act naturally on this root lattice. So yeah, and for each generator on Q, we have automorphisms of the field C over operational functions in alpha sub I. So the main feature of the affine Weyl groups is that we have Castro translations or translation operators. Yeah, and here we have some brief recall of them. So yeah, let me open the whole slide. Yeah, so for a translation operator, we need to consider the set of elements f sub I such that we can extend our representation of a affine Weyl group to the representation of affine Weyl group of skew field of rational functions in alpha sub I and elements f sub I. And if we can do it, then we can write down the discrete system as follows. So for each element from our lattice part, we define elements of this Q field, and the set of these equations can be regarded as a non-commutative discrete dynamical system. So yeah, and the main point here is that the extended representations can be found naturally from Bäcklund transformations of differential equations, in particular of differential Painlevé equations. And sometimes, and in the case of Painlevé equations, we need to work with extended affine Weyl group, and all this construction can be lifted to the extended affine Weyl group. Cool. So by using this approach, we can derive non-commutative analogs for discrete Painlevé equations of additive type. Yeah, by using this idea from continuous to discrete. Yeah, okay. Thanks to the paper by Berenstein, Grigoriev, and Shochkin, we know that matrix Hamiltonian Painlevé systems have Bäcklund transformations that form affine Weyl group structure. Now we can consider, we can reconstruct all the generators for these extended affine Weyl groups for non-commutative Hamiltonian systems that were obtained in this paper joined with Vladimir Sokolov. then we can use the same translation operators as in the commutative case in order to obtain a list of non-commutative discrete systems. And this list can be regarded as non-commutative as a list of non-commutative analogs for the discrete Painlevé equations of additive type. And at this point, I can say that equations from this list are related to each other by the famous coalescence cascade or by the degeneration procedure. So in particular, we can consider continuous limits for this system, and at this stage, we know only for several, not for all equations, but for several of them. And for example, the second Painlevé, the discrete Painlevé equation of E6 type and the discrete Painlevé equation of D6 type have a continuous limit to the second Painlevé equation, and it's another analog which is non-equivalent to the Hamiltonian second Painlevé equation. So at this point, I want to say that discrete Painlevé equations, even in the non-commutative case, can be considered as the most general object, because by using continuous limits, we can obtain the non-commutative differential Painlevé equations from the classification paper joined with Vladimir Sokolov. So how many time do I have? Okay, so we can similarly do this stuff for non-commutative dressing chain, and why we're interested in it, because dressing chain is a generalization of the Painlevé 4 and Painlevé 5 system to the higher order, and so we can produce the same stuff for non-commutative case. We can present Lex pairs. We can also present Bäcklund transformations, and thanks to the Bäcklund transformations for the non-commutative dressing chain, we can introduce the discrete systems. So last slide. About further questions, we can study. First of all, we can study the list of non-commutative difference Painlevé equations of additive type. In particular, there are Lex pairs, Hamiltonian form, continuous limits, also orthogonal polynomials, because they have non-commutative analogs thanks to the paper by Gelfand and Retech. We also can apply our algebraic method to obtain discrete Painlevé equations of other type, in particular of Q type, and it's also, I believe that it also can be applicable to the elliptic case. And two last questions about non-commutative geometry related to the Painlevé equations and their connection to non-commutative cluster algebras. Let me stop here, and thanks a lot.
Thank you very much. Questions?
The origin of the dressing chain is Darboux transformations for Schrödinger operators. So do these non-commutative dressing chain equations come from Darboux transformation of non-commutative Schrödinger?
No.
You
I know. I didn't study it.
You didn't try? Okay. It's worth doing.
Other questions? Well, I have one. If you can scroll back a few slides to before the dressing chains. Here, for example. So when you say dp E6, what is E6? Is it a surface or is it a symmetry?
Surface.
And what's the meaning of the surface in the non-commutative case?
I don't know. This is just a notation. It's just a label.
Okay. Questions? All right. Let us thank Ira again for a very nice talk, and have a coffee break.